Alrighty, so we're looking at this booklet here. 2.3, let's talk about velocity. In everyday language, we can use the words speed and velocity interchangeably. In physics, we make a distinction between the two. Very simply, the difference is the velocity is speed in a given direction. So velocity includes direction, right? Velocity is speed with direction. And I'm hoping you remember all those directional conventions, north, south, east, west, right? 30 degrees east of north, 40 degrees west, that kind of stuff. Do you remember the bearing method, how that worked? From way back when? Anybody? What's north in the bearing method? 0, and then you go, which way though? Clockwise, 90, 180, 270, and then of course that would be the same as 360. Do you remember that? North, east, southwest? Yes? Okay, remember that's different than those crazy math people that go like this, right? And they go 0, pi by 2, pi, 3 pi by 2. Have you guys seen that yet?
Oh, yeah.
Yeah? Oh, can you get more fun in the unit circle?
Yeah, you can do questions of all these in circle.
All right. So in physics, very simply, the difference is velocity is speed in a given direction. When we say a car travels at 60 kilometers an hour, we are specifying its speed. But if we say a car moves at 60 kilometers to the north, we are specifying its velocity. Speed is a description of how fast, velocity is how fast and in what direction. We will see in the next section that there are good reasons for the distinction between speed and velocity. So here's a couple quick questions. The speedometer of a car moving northward reads 60 kilometers per hour. It passed another car that travels southward at 60 kilometers an hour. Do both cars have the same speed? And the answer is yes, they do, because they're both traveling at 60. Do both cars have the same velocity? No, why not? Different directions. In fact, you might say that one would be plus 60 and the other one would actually be minus 60, right? What does the positive generally indicate for a direction? North or east, right? Left, right kind of thing? Okay, so it's sort of dependent upon that, right? You do have to watch for signs. There will be many of you that say at times, do I have to worry about the signs? And I'll say, no, in this question you don't. Sometimes you do. And when you get a no, you're not. You're just going to have to know when to know to worry about it. And I know that's going to be a problem for some of you. But with experience, it'll come. Know when you need to worry about it. Okay, constant velocity. From the definition of velocity, it follows that to have a constant velocity requires both constant speed and constant direction. Constant speed means that the motion remains at the same speed. The object does not move faster or more slowly. Constant direction means that the motion is in a straight line. The object's path does not curve at all. Motion at constant velocity is motion in a straight line at constant speed. Changing velocity now. If either the speed or the direction or both is changing, then the velocity is considered to be changing. Constant speed and constant velocity are not the same. A body may move at a constant speed along a curved path, for example, but it does not move with constant velocity because its direction is changing every instant. Can you give me an example of an object that might be moving and changing direction? What was my question? Give me an example of something that as it's moving at constant speed. So you said a race car. In what sense? Well, is it a straight racetrack?
No.
Okay. One of those oval kind of things, right? So yeah, if you're traveling around the track at a constant speed, if you got that, do race cars do they put the cruise on?
No.
No, they don't, right? In fact, they probably slow down when they get to the corners, right? A little bit, right? But yeah, I suppose that's true. If you happen to be on a racetrack with the cruise on, maybe you're the pace car, right? And you're setting that constant speed, that kind of thing. Okay. In a car, there are 3 controls that are used to change the velocity. One is the gas pedal. What are the other 2, do you think? Steering wheel and brake pedal, I heard? Yes. The second is the brake, that would slow you down. And the third one is the steering wheel because it's used to change the direction. Have I successfully differentiated between constant and change in velocity? Covered it all. Think so. Hopefully none of that was too new for you. Okay, let's ramp it up a little bit here, and let's talk about acceleration. We can change the state of motion of an object by changing its speed, by changing its direction of motion, or by changing both. Any of these changes is a change in velocity. Sometimes we are interested in how fast the velocity is changing. A driver on a two-lane road who wants to pass another car would like to be able to speed up and pass in the shortest possible time. The rate at which the velocity is changing is called the acceleration. Highlight that for me. Not for me, do it for you. The rate at which velocity is changing. Okay? A lot of people confuse acceleration with velocity. It is the rate at which the velocity is changing. Where was I here? Thank you. Because acceleration is a rate. It is a measure of how fast the velocity is changing per unit of time. And there is the formula that you no doubt remember from grade 11. Acceleration is change of velocity over the time interval. We abbreviate it with a delta V over delta T, where the triangle delta thingy represents the idea of change. Change in velocity over change in time. I would like to point out at this point, because so many people get it wrong, it's not on here, but I would like to point this out. Do you remember what that's all about? Remember me talking about that lots in grade 11? Many of you maybe had it on a test or two. Okay, what's the difference between delta V and V bar? One is a change, the other one is? It's not necessarily a constant. It could be average. Okay, and I always give an example with tests. Let's just talk about this. This is so important, you guys, and pardon me if you get it. Just give me a few seconds to get this out of my system here. Let's say you've written two tests. You've got a 70, and let's say you smartened up for the next one, you got an 80. What is your average? 75. Everyone can do that in their head. What is your change? How much did your mark change by? Plus 10. Those are different. Right? Completely different. I think everyone gets that. Now, let's say you're driving at 70 kilometers per hour, and then you speed up to 80 kilometers per hour. What is your average? Again, 75. What is your change? Plus 10. They are different. Different. And even though you nod, you go, yeah, I get that. That makes perfect good sense. I know that I'm going to see some of this coming up, right? You've got to get that straight. And I think the biggest problem is people want to abbreviate. They want delta V and V bar. They just want them to be V. It's just V. It's velocity. No problem, right? It's velocity. But then they make this mistake. So please include the delta V and please include the V bar. Rant for the day. I think Rick Mercer should do a rant about that. Me and about 27 other people get it. Flip page. We're all familiar with acceleration on an automobile. The driver depresses the gas pedal, appropriately called the accelerator. Passengers then experience acceleration or pickup, as it is sometimes called, as they tend to lurch toward the rear of the car. The key idea that defines acceleration is change. Whenever we change our state of motion, we are accelerating. A car that can accelerate well has the ability to change its velocity rapidly. A car that can go from 0 to 60 in 5 seconds has a greater acceleration than one that can go from 0 to 80 in 10 seconds. Even though one car can go up to 80, that's a greater speed than 60, right? You think, hey, greater acceleration. You'd be wrong. Right? It has a greater top end, but that doesn't mean that it's accelerating more. So having a good acceleration is being quick to change and not necessarily fast. You might want to highlight just that little phrase. Quick to change. Right? Acceleration means quick to change. Give me an example of an automobile that is quick to change its velocity. It doesn't have to be a specific make and model, or year, or color. Dallas says a Pontiac 6000. Not real familiar with that vehicle. Explain why that car accelerates fast. Is it because it's the one you're driving and you got a limp foot? Yes. Pardon me? It's not that fast? It might be a better example of one that's not that. Okay. Maybe it doesn't necessarily have to be a car. Give me an example of a motorized vehicle that goes from stop to really fast, really quick. A motorbike. Motorbikes tend to go from like stop, fast, really quick, right? Especially those race ones, right? Okay. Things like semis and Pontiac 6000s, they go from 0 to 100, but it takes them a long amount of time to get up to 100, right? The motorbike goes from 0 to 100 like in 3 seconds. Dallas goes from 0 to 100 in about 4 minutes. Is that true? Just making fun of that. Okay, so does that make sense? Yes? Yeah? I'm hoping it's reviewed. In physics terms, the acceleration applies to decreases as well as increases in speed. The brakes of a car produce large retarding accelerations. That is, they can produce a large decrease per second in the speed. This is often called deceleration or negative acceleration. We experience deceleration when the driver of a car or bus slams on the brakes and we tend to lurch forward. Acceleration applies to change in direction as well as change in speed. If you ride around a curve at a constant speed of 50 kilometers an hour, you feel the effects of acceleration as you tend to lurch towards the outside of the curve. You may round the curve at a constant speed, but your velocity is not constant because your direction is changing every instant. Your state of motion is changing, you are accelerating. Now you can see why it's important to distinguish between speed and velocity, and why the acceleration is defined as a rate of change of velocity rather than speed. Acceleration, like velocity, is direction, and therefore it is a what kind of quantity that we all love and just couldn't wait to get more of? Vectors. Remember the little vector dude from Despicable Me committing crimes that have both size and magnitude, I think, right? Is that what he said?
Direction.
Size, oh, yeah. Right. Size is magnitude, like how dastardly the crime is. If we change either speed or direction, or both, we change velocity and time. When you're driving around the corner at St. Rose, you know, you've all been around that corner, I'm sure, at least once in your life. You got the cruise set at exactly 100, because you'd be foolish to go faster than that. And as you go around that curve, you are changing your velocity, changing your direction, and thus you are accelerating. Here's some foreshadowing for you. What direction is the acceleration? There has to be a vector, there has to be a pointy thing pointing in some direction. As you go around the curve, to the right, he says. Let's say you're driving from Oka River, and you're making the curve. This way is Neepawa and McCreary and all those good places. And here's St. Rose, and you're traveling this way. Which way is the acceleration? I'll give you a few options. Is it black arrow? Is it blue arrow? Is it red arrow? Or is it crazy yellow red line arrow? Oh no, didn't do that. That way. Which way is the acceleration? You got 4 choices. Give me a color.
Blue.
Blue?
Looks like
How many people say blue?
just me. Can't give me an answer.
Yeah. Well, okay. You don't have a lot of company though. How many people say black? How many people are physically able to put their hand above their head? Thank you. Okay, let's try again. How many people say blue? Well, I'm asking for the acceleration. You're a bold man, Daniel. Blue. Black. Red. Crazy red and yellow. Again, how many people can put their hand above their head? Come on, you guys. You got to be brave. Daniel's right. The acceleration is towards the center of the circle. Good for you, man. Give yourself a tap for that. There, give him a little tap for that. Say, way to go. Well done. More on that when we get to circular motion. Don't worry that you don't get that.
The reason I know that is because Mike told me that.
Who told you that?
Mike,
Oh, yeah?
we were going to.
That's a bunch of junk. Tell him thank you. I forgot to show you what he wrote on my exam.
Oh, yeah.
I'll show you that. Okay. Where am I here, you guys? Am I at that paragraph right below the picture? I think so, eh? Did I finish that one? Yeah, I did. I finished that one. Okay. In most of this book, we'll be concerned only with motion along a straight line. When straight line motion is being considered, it's common to use speed and velocity interchangeably. So when you're just going like a drag car or train or whatever, and you're only going forward and backward, speed and velocity, not a big deal, right? Because it's just plus forward, negative backwards. We don't get too excited about it. But when we get into things like rounding curves and projectile motion like baseballs and footballs going like that, and Evel Knievel jumping over rivers full of sharks and stuff like that, it's important. Okay, and you just have to sort of, oh yeah, this is one of those important things. I know this. So acceleration can also be change in speed over time interval. Okay, speed and velocity are measured in units of distance per time. The units of acceleration are a bit more complicated. Since acceleration is the change in velocity or speed per time interval, its units are those of speed per time. If we speed up without change in direction from 0 to 10 in 1 second, our change in speed is 10 kilometers per hour in a time interval of 1 second, and our acceleration is 10 kilometers per hour second. Now that's a weird thing. 10 kilometers per hour second. And there's a little dot there indicating multiply. It's kind of a weird unit that you can't really wrap your head around, right? It might be easier to say 10 kilometers per hour per second. That makes more sense, right? Sort of conceptually in your brain. I'm changing my speed by 10 kilometers per hour per second. In other words, every second my speed increases by 10 kilometers. If Dallas is at a stoplight in Pontiac 6000, and you know what, this is going to be like common theme for the whole unit. It's going to be awesome. Are you happy with that? Not so much? Okay. So Dallas is at the red light in his Pontiac 6000, right? He hammers on the gas, and every second the car, after 1 second the car's going 10 kilometers an hour. And then another second later, it's now going 20 kilometers an hour. And then another second later, it's going 30 kilometers an hour, and so on. Meanwhile, Jake's driving his little Kawasaki, and he's up to 100 in about a half a second. Maybe Jake's dad got in a Camaro and he's out testing it out or something. Does that ever happen? Dad ever get in a Camaro and you get to test it out? Okay, the acceleration is 10 kilometers per hour second. Note that a unit for time matters twice, once for the unit of speed, again for the interval of time in which the speed is changing. If you understand this, you can answer the following questions. If you don't, maybe the answers will help. Flip the page over. Now, do you see the answers there? Right on the page? Cover them up with your hand or something or other, right? Let's not give them up here. Okay. Suppose a car moving in a straight line steadily increases its speed each second. First from 35 to 40, and then from 40 to 45, and then from 45 to 50. What is its acceleration? So every second it goes from 35 to 40, and then 40 to 45, and then 45 to 50. And that's happening in 1 second. So what is its acceleration? How much does it speed up by each second? 5 kilometers per hour per second. 5 kilometers per hour per second. Question number 4. In 5 seconds, a car moving in a straight line increases its speed from 50 to 65, while the truck goes from rest to 15 in a straight line. Which undergoes the greater acceleration? We go from 50 to 65, and the other vehicle goes from 0 to 15, both in the same amount of time. Which one has the greater acceleration? They are the same. They are, in fact, 15 kilometers per hour. Is it 3 seconds? 5. Oh, good thing. 3 kilometers per hour per second. It doesn't matter whether you're at rest or whether you're already going 50. Your acceleration is the same. Now, is that how vehicles really work? They have this thing called the gearbox in there, right? That changes things, right? You can go from 0 to 15. That takes a different amount of time than going from 50 to 65 just because of the way the vehicle works, the gearing, okay? This is sort of a very simplistic situation.
Could not be argued that the truck would be more powerful because it has to overcome friction. What was the friction called?
Okay.
Starting friction.
Yeah. Starting friction, remember, the deal with friction is that all the friction we talk about in here is sliding friction. Once you get into rolling friction, it's a whole more complex kind of thing. So yeah, and what do you mean by the word power? Is power related to acceleration in some way?
Really crappy engine. Very well.
Like powerful cars like the Charger you were talking about tend to have a good acceleration. They can go from 0 to top speed very quickly, right? Yes, power is related to acceleration. Power is, and this is way in the future, power is equal to work over time, and work is related to distance and force and blah, blah, blah. And okay, yeah, basically powerful engines can accelerate really fast. Okay. I think I'll stop talking. Are you tired of listening to me? Probably a little. I'm tired of listening to myself. Okay? There are, at the back of this last booklet here, there are questions. It says 1 to 10, but I think I cut some out. So there's 1, 2, 3, 4, 5. 6 is gone, 7 and 8, and then 10. Okay? All of the answers should be found in these 2.5 pages. Okay? How about I give you, I'll give you about 10, 15 minutes to do a few, then I'll give you some answers, then I'll give you some time to finish. How does that sound? Is that good? You guys need more light there? Any good over here? Yeah? Okay, you guys are good with the light over here? Okay. Awesome. Okay. Number 1A, define acceleration verbally and mathematically. So verbally they want something like acceleration is the change in velocity over time, and in a mathematically they want something like A equals delta V over delta T, something like that. What type of quantity is acceleration? It is a vector quantity. And what is deceleration? Yeah, or you could even say negative acceleration. I try not to use the word deceleration. It can be a little bit confusing, because what if the car is going in the negative direction and slowing down? Which way is the acceleration? Positive. The car is traveling, the hat on wheels is traveling to the left. I never took art in class in school, yeah, can you tell? If the car is traveling left, then the velocity is negative, and if it's slowing down, then the acceleration is positive, isn't it? But is it decelerating? Well, slowing down, so I try not to use the word deceleration. A certain car is accelerating at 5 kilometers per hour per second. Explain what's happening to the motion of the car. You should have something like every second the speed is increasing by 5 kilometers per hour. Right? 5 kilometers is the distance taken, right? Oh, good. I believe. Did I cut you off? Is that what happened here? Yeah. Oh, I apologize. Give an example of a moving object that has a velocity vector and acceleration vector in the same direction. So velocity, acceleration in the same direction. V and acceleration, same direction. Would be a car doing what? And accelerate. Moving in a straight line and accelerating. What about opposite directions? A car moving in a straight line and slowing down. Slowing down. Can an object be moving at a constant speed and accelerating? And I've given you an example of this already today. Can an object be moving at a constant speed and accelerating? Yes. What would be an example? Or what would be the one that I told you earlier? Go around the curve at St. Rose on cruise control, right? What would be the shape of a speed versus time graph for an object in free fall? Speed versus time graph. Okay, so time, speed, so in other words, it's all positive because there's no direction. In free fall, so it falls and it speeds up faster and faster and faster, so what would the graph look like? It'd be like this? Or would it be like this?
If there was no air resistance or anything, it'd be the graph on the left.
Correct. There's no air resistance, it's the one on the left. It'd be increasing at a constant rate. And in fact, what would be the slope of this line? Well, because it's positive, it wouldn't be negative, I guess, right? Because we're talking about speed here. But it would in fact be 9.8, wouldn't it? Right? If there is some air resistance, Jake, what does it look like? Like that, right? It reaches a terminal velocity, right? It reaches some speed that it doesn't get any faster than. Is that all good? I'm going to pause there and let that sink in for a minute. Are those awkward pauses when teachers do that? Sometimes? It's awkward standing up here for it too. That's not just sort of talking about nothing right now. What is the relationship between speed and velocity? Velocity is simply speed with a direction. Very good. David. Answer the following by referring to figure 3.5, which is back a little bit. 3.5 is that sort of curvy one there, right? Well, I know. That one, right? Over which interval did the object have its greatest velocity? When does it have its greatest velocity? In other words, this is position time, d versus t. So when is it its steepest? Yeah, C to D for sure. Right in there. C to D, it has the greatest velocity because the slope is the steepest. Over which interval was the object's velocity decreasing? When is the velocity decreasing? From D onward, says Dallas. Would you agree with him?
Yes.
And you would be correct, right? Decreasing, D-E-C-R. How can you tell? Like, how do you know it's there, Dallas? What does? What quantity is decreasing? Because the line is still going up, is it not?
It's not going up.
The slope. Is that what you're trying to say?
Yeah.
Yeah. The slope is flattening out, so it is slowing down. Very good. Over which interval was the speed increasing? When is it speeding up? Right here, right? 0 to, what is it? Well, 0 to 6 exactly, right? 0 to 6, it's increasing in speed. How can you tell? Because the slope is getting steeper. Is it all coming back to you now? Is it starting to come back to you? Number 10, sketch a graph of motion, distance as a function of time, that would correspond to the following bicycle trip. So they want you to draw a displacement versus time graph. You start your bicycle from rest and increase your speed until you reach a comfortable traveling speed. You continue at the speed for a few minutes and complete your trip by slowing down uniformly to a stop. So we're going to speed up, so it's going to be curved, and then you travel at a constant speed, so it's a straight line, and then you stop. So how do I show stop? Yeah, I slow down and I become not like that, right? Is that good? Yes? Yes? Awesome. Okay. We'll leave it there.